Risto. Thank you. I want to introduce Risto Miikkulainen. Is that how I say your name? I'm sorry if I butchered it.
Miikkulainen.
Okay, thank you. Who is a professor at computer science at the University of Texas at Austin and associate VP of evolutionary AI at Cognizant. He received an MS in engineering from Helsinki University of Technology, now Aalto University, in 1986 and a PhD at UCLA in 1990. His current research focuses on methods and applications of neural evolution. In fact, he just had a couple nice papers on neural evolution in the past 2 years or so, as well as neural network models of natural language processing and vision. He's a IEEE Fellow and received an IEEE CIS Evolutionary Computation Pioneer Award, a Gaber Award from the International Neural Network Society, and an Outstanding Paper of the Decade Award of the International Society for Artificial Life. With that, I will let you take it away, Risto.
Yeah, great. Thanks, Keith. Just want to make sure that you still see my title slide because the green boundary has disappeared from my screen.
Yes, what's your title slide?
Okay, great.
Your title?
Excellent. Yeah, so I'm going to talk about this new approach on technology with lots of applications called Evolutionary Surrogate-assisted prescription. This is actually mostly done at my research group at Cognizant. These are my colleagues there, although a couple of these people are also my former students and current students. Santiago is my current student, Elliot is a former student at UT Austin. So the big picture is this: how do we make good decisions in all aspects of life? There are now organizations that have recorded of what they actually do. All kinds of businesses have data: hospitals, healthcare, markets. We have data about students and what they do and how they learn. So we can build models based on that data that predict what will happen in the future, given some situation. But these models do not tell us how to make better decisions. They just predict what will happen if you make a decision. So it's a different problem to figure out what we actually should do. And that's what I'm focusing on getting to that next step from prediction to decision-making, from prediction to prescription. So it is not easy. It has its own challenges. First and foremost, we don't know what the optimal decisions are. Unlike in maybe prediction, we can look at historic data and see how the time series unfolded in weather or pandemic, for instance. But we don't know what the best decisions might be because we haven't tried all of them and we haven't observed what happens. And also the domain is usually not completely known. There are factors behind the scenes that we can't really monitor. And many of the factors that make or come to the decision-making interact and non-linearly. So some variable may have a very different decision based on another variable. So the standard approach has been for decades linear programming, and that can work, but currently if you go to the real world and ask people what they do with LP, they have a huge system of many different linear programming models because they can only linearize very small regions of it. And it's become very unwieldy in, say, optimizing manufacturing processes or something like logistics. And also the gradient descent methods that we have taken great advantage of in AI, they cannot really be applied when you don't have targets, when you don't know what the optimal decisions are. So instead, we need to search. And that means trying out alternatives and see which ones of them work and learn from that. Do more of this because it works better than something else, and explore areas of decision-making strategies where you hope to find some good ones. So it's called search, which sounds very weak, and it is, but we have very strong methods now of doing the search efficiently and solving real-world problems with it. And that's what this talk is about. Now, one way of doing this kind of search is that you interact with the real world, you try out your alternatives in the real world. Well, that can be a little costly. If you're doing treatments and diseases or maybe marketing or design of rockets, you cannot really afford to make mistakes. So you have to have something else. And simulators are a good idea if you can build one. If you can, in some cases in engineering design, you can build a simulator of what the design would be in the physical world and how it would interact with the physical world. But it's hard to build those, and it's costly to build them and run them. So there's an alternative. Let's build a model instead of the simulation that's just a phenomenological model. It's based on data, past history, what happened in the past, and we just trying to model that without necessarily even understanding why it happened that way. So here's the diagram of that. This is the decision-making framework, and we have two models here. The surrogate is the prediction model, and that is a surrogate of the world. We are looking at a decision-making context, the problem that's given to us, and then we are making some decision in that context, like allocate your marketing dollars this way, or set up your aisle in a shopping market this way, or do this kind of a engineering design. And then we use past history of this context, this action, and how it turned out to train a predictive model. So you have to have historical data about decision making in the past, many different contexts, the different actions that were performed, and then the outcomes that were collected, how it turned out, in order to train this predictive model. But if you have such data, you can use that predictive model now as a surrogate. You don't have to try out new ideas about what decisions should be made in the real world. You can just ask the predictor, how good do you think that this decision would be in this context? And it gives you the estimate. And then we can search for a good decision strategy, this horizontal model here, one that maps contexts to actions. We can search, use the surrogate model to search for good such policy or strategy and make good decisions in the future. That's the idea of surrogate optimization. Now, it's still a hard problem to do that. The search space for those strategies, trying to find some way of deciding what to do in the future in those different contexts, it's a difficult problem to find those strategies. The space is still nonlinear. It can be deceptive, look like this. If you try to find a maximum in a space like this, it's very hard compared to something like this where you can climb a couple of hills and find a good one. It's a very high dimensional. It's multi-objective. You have usually a cost and you have a performance and you have to balance them. And there are many different factors that you have to take into account. So for instance, kriging and Bayesian optimization, which in principle can approach this kind of decision-making optimization, they don't really scale beyond just 10 or 15 variables. But we have a lot more in many of these decision-making tasks. They might have hundreds or hundreds of thousands, depending on the design problem. Now, reinforcement learning could be used in principle because it is also a search methods, exploration methods, trying to find by searching locally and making small steps, something that works well. But it is difficult to scale it up as well, especially in these very large, very high dimensional, multi-objective landscapes. We don't currently have reinforcement learning methods that would scale that way. So that's why we bring in evolution, or surrogate-assisted evolutionary optimization. That means that we have a population-based search method. We drop a whole population, hundreds of individuals into this landscape and search simultaneously, and the individuals communicate partial solutions. That's the idea of evolution. You do recombination of partial solutions in order to find good ones. And that is actually something that makes this work, makes the approach scale up. The population-based search can be more exploratory and it can find solutions to really hard, really large problems. Now, there's been quite a bit of work already on surrogate-assisted evolution, but most of the time, the idea is to find one single point, which is pretty much true of kriging and Bayesian optimization as well. But what we need to find, if we want to find a decision strategy, is actually a representation of the whole strategy, not just a single point that optimizes the surrogate, but a strategy that tells you what to do in future situations and future contexts. So therefore, what we're looking for is a neural network for instance. So it could be something else, but it's a mapping from context to actions. So we use neural networks and we find them using evolution. And that's what I'm going to talk about. That's the technique in the title, Evolutionary Surrogate-assisted Prescription. So prescription is the decision making recommendations. We use a neural network for the surrogate. It could be something else. It could be random forests, and some of the examples later we have random forests as well. And we evolve a neural network to be the prescriptor. So predictor is trained with backprop because we do have historical data. The prescriptor must be evolved because we do not know what the optimal actions are. So that's how we put this together. And there are many variations, but the general setup is the same. Historical data is first used to train the predictor as a surrogate, and then evolution used to train the prescriptor to make the decisions. Now, we've had these components for quite a while, and we have actual real-world applications of both elements that make ESP. This picture here in the middle is about CyberAg, and a project at MIT Media Lab where they built these containers where everything is controlled. The temperature, the nutrients, water, different kinds of light, UV light, everything that goes into a container is controlled. And now the question is, how do you come up with the best recipes for growing plants as efficiently as possible and also making them as tasty as possible, or whatever your objective function is. So here, we are using a surrogate for the real world because it's very costly to plant something and watch it grow. That might take several weeks. We have about 3 weeks for basil. Pecan trees might be 200 years. That's a little bit outside of scope right now, but we could do basil. And we planted a bunch of them, a couple of hundred, and built a surrogate model that then predicted what would happen with some new recipes. Then we used evolution to discover those recipes. So there was a surrogate model and a direct evolution of the recipes. There was no strategy, no mapping, no context. On the other hand, we had this application, which is designing websites so that the users who come to the site, they are most likely to click on that button, which is an action button, sign up, buy something. This in particular one was on educational programs, so find out more about this particular program. So here, there was a context and action mapping. So different users coming to the site would get different web page designs. We know something about them, what day it was, time of the day, what operating system they were using, what their geolocation was. And it turns out that you can optimize the page towards a person, depending on what you know about them. So we had this part here, but then the actions did not use the surrogate. They were just the designs themselves, and we tested them in the real world in real time, 2,000 users or so, to get the evaluation. So that was this bottom part. And now with ESP, we put those together and have a general approach to optimizing decision-making in many applications. So that's the historical background. Now, let's look at what components are and how they work, and we'll have a couple of evaluation examples and then one real-world example that I like to talk about, and do a live demo, interactive demo on it. So the prescriptor is the real meat. That's something that is rarely there in the real world. A lot of people build predictors, but prescription is something a little different. So that's the idea, optimize the outcomes given a context and producing an action that optimizes them. So this can be a neural network, or it can be a set of rules, or it can be something else. But we use neural networks because we have a long history of evolving neural networks. And actually, last time I gave a talk at ISI, it was about that, about using evolution to optimize architectures of neural networks so we would get best possible performance. So this is a mapping from context to actions, but actions are not no, so therefore we have to evolve them and evaluate each candidate using the predictor. So the predictor then is a standard machine learning approach. It could be a neural network, which is what we use. We know how to train them, backpropagation, stochastic gradient descent. They could be deep learning networks, but a lot of times the problems are not yet large enough. We don't have quite enough data for deep learning, not millions of examples. We might have thousands of examples or tens of thousands. But most importantly, it is usually a multi-objective problem. So we need to train a neural network to predict not only an outcome as a performance, but also a cost and maybe some other variables. So we get a multi-objective evaluation of how good our actions are and how good our strategy is. Now, putting this together in an application means that we have a loop with the real world. Now, if we are really lucky and the application already is built based on a database that somebody has collected the data about decision making, maybe it's marketing decisions in a business for last 3 years, we already have that data set available. Then we can immediately use it to train a predictor. Once we have a predictor, we can evolve the prescriptor, and then we can just deploy the prescriptor into the real world, where it starts to prescribe actions and we never actually have to do anything else. But there's an opportunity, once we have this prescriptor deployed, to collect more data. What is actually now done by the prescriptor becomes new data samples. We can augment the data set with it and retrain the predictor to be better, retrain the prescriptor to be better, and have a loop. And it could happen a couple of times. It could happen regularly. This is something we actually, an example of optimizing COVID-19 interventions. We do this over and over again every day. In some other cases, like the web page optimization, it would happen every few months. And in some other cases, you might never actually have to do it again once you run it once. But there's an extension to a very tight loop, something where you have to make many decisions in order to see the outcome, the sequential decision-making task, like a game-playing task. And there you have to start from the bottom. You have to start with a prescriptor that's perhaps initialized randomly or using some set of rules to imitate them. And you run it in the real world and you get data after the deployment of the prescriptor. Then you use that to train an initial predictor and immediately improve the prescriptor, put it back into the real world, and you're in a loop that's very tight, happening all the time. Now, this is interesting. There's a surprise, and I already give it away. I show a demo later how it happens. But there's a synergy here, interesting synergy, that when you are co-learning the predictor and prescriptor in this tight loop, they both start as very coarse approximations of what eventually needs to happen. And what happens is an automated curricular learning. The predictor starts very simple and it becomes more and more accurate, resulting in better prescriptors. And the prescriptors are evolved against many predictors. So there's a regularization effect that happens. So there's a synergetic effect on learning both at the same time, starting with little data and gradually making the components more accurate. So we'll see an example of that soon. Now there's one more element that we have to address if you want to do anything in the real world. And that is trustworthiness. If you actually want somebody to use your decision-making system to allocate money to marketing channels or decide what to do, whether to close the schools in order to mitigate pandemic, you have to give estimates of uncertainty. How well can you trust this decision or the outcomes of the decisions? What is the confidence interval around your predicted revenue, for instance? So we need to develop some technology to do it. And this was really driven by the real world need. So the question is, when we make a prediction like this, we predict value, cost, the side effects of a drug treatment, can we trust it? What's the confidence interval? So it turns out there's a way of doing that. And this took quite a bit of work to figure out, but if you have a neural network that's predicting a variable, a continuous like regression variable, like cost or revenue, you can build another model using Gaussian processes to model the residuals, the error that still remains after you run your neural network. And the Gaussian process has a little bit different biases, so they complement each other. And you can actually use the confidence intervals from the Gaussian process to evaluate how confident you are in the decision. And then you use the mean of the of the distribution to correct the output of the neural net. And this was a big surprise, that you train as much as you can. You train a neural net to be very accurate. You can still improve it by training a Gaussian process to model its errors and fix some of those. So that's a different line of research, but it was very useful because we can apply it to these decision-making systems, and the users can actually get an estimate how well they can trust the result. There's another way of making a system trustworthy, and there's also a demo later, and that is that when we make a prescription, you have a user decide whether to apply it or whether to modify it or do something completely different. We are doing this in order to help human decision makers, and we have to make it possible for them to bring in their domain knowledge, their expertise, their idea of what should be done. So here we have a Scratchpad. The prescriptor makes a suggestion, and you can go with the Scratchpad, modify it, and then you can get predictions of how well your modifications would work. And maybe you find something that's a modification that's better. Great, you can deploy that. Or maybe you try all the modifications you can think of and find that the prescriptor is the best that can be done given the predictor. And then you trust it, that this is indeed probably the best one, and you deploy it. It turns out in real world, this kind of exploration based on what AI gives you is really important for people to trust the AI. And it's pretty easy to do, that Scratchpad. What's really useful is that we have an interface to the predictor. So any modifications you can evaluate and see how well they work. All right, so let's get into some examples. We start with something that's simple, but on the other hand, easy to visualize and understand. So we can really show what happens in this process when both predictor and prescriptor are learning at the same time. So here, the task is very simple. Your context on the bottom left of that triangle or state is in the x-axis, varies from -10 to 10. And then we have the action, the decision, that also is a single number, varies between -10 to 10. And here we are plotting with the color coding the optimal decision policy. So the brighter the color, the better the value of the action is. So for -10, you want to do something about 4. And then for -4, you want to do maybe -3, and so on. So this tells you what the optimal actions are. We know the ground truth. We know the best possible policy in order to just visualize how the learning can discover it. And here, we are actually plotting the different components of ESP and how they work. So we need to use samples, the data set from the real world, to train the predictor. So these little circles are the samples. So we sample the real world. For this context, we've sampled the action -10, that's 1 point. For this context, about 8, we sample the action of -8, that's another data point, and so on. And we get how good the value is using this color coding. So those are our samples we use to train the predictor. And then while predictor is learning, we also train the prescriptor. So the current predictor is in the background color here. And after 25 episodes, which means those samples, we have a predictor that's kind of in the middle, but it's not nearly accurate yet. It doesn't look like a sine wave. There are some strange things up here, for instance, that are deemed to be highly valuable that really are not. So it's not very good yet, but you can see the color encoding of what it is. And then the prescriptor is trained against that predictor. And the current prescriptor is this orange line. So given these contexts in the X, this is what the prescriptor tells you to do in Y. So it's almost always like about -1 or so. And the other lines are also very interesting. So we know what the optimal predictor is. This is that dashed line here. That's the sine wave. But there's also the concept of, given the current predictor, what would be the optimal prescriptor for that predictor? We return the maximal values. And that's the white dotted line. And you can see that it looks kind of funny. It goes all the way up here. So it's not nearly the same as the actual optimal prescriptor. So our predictor is leading us a little bit astray. It's not really accurate yet. And the idea is that over time, the background should become a sine wave, and therefore also this dotted white line should coincide with the blue dashed line. And then our prescriptor should also follow that sine wave. All right, so with that, let's see how that works. Here's an animation that starts by adding points gradually. And as you see, it's very inaccurate. The background is still quite inaccurate. The predictor is inaccurate, but already the prescriptor is surprisingly accurate, given that our predictor is not actually working that well yet. And eventually, we do converge to a very good prescriptor, very good sine wave, so that both the predictor looks like a sine wave a little bit. There's still some inaccuracies here, but mostly it's a sine wave. The dotted white line, the optimum of that background, is coinciding with the sine wave, and so is the prescriptor. But notice early on, there are these situations where the predictor optimal line is very different from the sine wave, but as you see, the orange line already starts to approximate the sine wave, much before the predictor even converges. So this is fascinating. Why is that happening? And the reason is, we eventually figured it out, is that when you are evolving the prescriptor, you are evaluating it over time across numerous different predictors. So it's like evaluating it against an ensemble, and they all together favor prescriptors that are optimizing the actual underlying function. So there's an automatic regularization by ensembling those predictors. And that was a surprise. We didn't anticipate it, but it turns out that this kind of co-learning of the predictor and prescriptor gives you that in evolution, because you have to evaluate multiple predictors and prescriptors, you get that regularization effect. Okay, now let's see how well this actually works compared to some of the other methods. These are some snapshots from that evolution and training. And on top we have comparisons. This is direct evolution, not using the surrogate at all, just evolving the prescriptor, the orange line. And even after 1,000 episodes, which is much longer than here, 125, we're still not learning it. It's very hard. The predictor serves a purpose. It starts simple and therefore gives a curricular learning challenge, and we get this sine wave much quicker than when we try to evolve it directly. And the other comparison here is a standard state-of-the-art reinforcement learning methods, PPO, and we are here counting the same number of episodes, like how many times you tried in the real world, and it will eventually learn, but it's also even at 1,000 episodes, it's also pretty far away from actually learning. So we can now plot some performance plots here. This is ESP, the surrogate-based optimization using evolution neural networks. It's very fast, and it's very accurate and has very low variance. This is direct evolution. It's not doing that well and varies a lot. And this is PPO. It has higher variance and it takes longer, but it will eventually get to almost to the same point. And this is regret, measuring how costly it is to do these evaluations. And here you see that the regret drops very fast for ESP, and there's significantly more for PPO and direct evolution. So this kind of surrogate optimization with evolution is faster, more accurate, it's more reliable, and also it has a lower cost and it's safer. But this is now in this artificial domain of function approximation. We've of course tried it in other domains. This is one of the standard reinforcement learning benchmarks from OpenAI Gem, the CartPole version 0. And here we have exactly the same comparison, but in a different task. So here's ESP. It has lots of variance originally, but it does converge very quickly. And here, direct evolution actually works pretty well compared to PPO, but PPO eventually catches up, as does DQN. But DQN has a very high variance. So again, those dimensions of speed of learning, reliability, variance, ESP is much better than these reinforcement learning benchmarks. And here's regret again, the same kind of result. The regret is very low. So that's a comparison and a benchmark that everybody knows, and there are many implementations, and we can do the comparison. Now, but let's try to do something a little more interesting, one step at a time. So we go from a synthetic function approximation to a game playing domain, and then to a real world application on the COVID-19 pandemic. So there's another way that surrogates happening. Previously, the regularization is happening. Previously, it was because we are ensembling multiple surrogates. But there's also the idea that the surrogates learn gradually. And even though the landscape may be kind of complex, the early surrogates are simpler, and that gives you more regularization in evolving the prescriptors. So we are now starting to understand regularization better. There are lots of papers coming out in all kinds of approaches that are finding that regularization is really the key in making neural networks and deep learning work. And there are many methods for doing that, and many methods that are not intended to do regularization, but turns out they are, and that's why they are working well. And one of the conclusions that's emerging is that very early on in late learning is when regularization matters. So early learning has to be simple and regularized, and then later on you can do more fitting, more tight fitting. And that turns out that that's happening here automatically, because we are training the predictor. Initial predictors are only getting the coarse picture right, and then later on get more of the details, and that's perfect for regularization as well. But it's a different mechanism for regularization than we looked at before, where we were using multiple predictors that were all inaccurate, but as an ensemble gave you an idea what you need to do. So that's important to point out, it's different. And here's the domain for this next step. It's Flappy Bird, and you're probably familiar with it. It's one of the traditional classic games. You have this bird that has to fly through an obstacle course of these pipes that have a gap in the middle, and you can flap, and a flap causes the bird to go up, but you have to avoid those pipes. Here's the summary of the results already with direct evolution. Direct evolution has very hard time learning this task because there are strong nonlinear interactions in the domain. The physics is hard, and you get stuck with suboptimal solutions, and you overfit to them. But this is where the prediction surrogate comes in, the regularization comes in. So let's look at a video or movie animation of how the surrogate actually sees the world, what it's trying to reward. And it was easy in the previous example where we have a function approximation. But here in the game, what does it mean to give an easier challenge? So we're actually visualizing what the predictor thinks the game is. And it's a little different from the final game. So initially, the predictor only gives a challenge of getting through that first opening. So it gives different locations for the opening. But once the bird gets through the opening, it very much slows it down so it can figure out what to do after flying through it. And now it also brings in pictures of the other pipes, because you have to start thinking about how you meet the next pipe after flying through the first opening. And then after it gets that right, it gives you this challenge of just flying straight. The pipes are all in the same location. And once that's working, it actually starts to move the pipes around where they really are. And that is more or less the actual game. But it gradually becomes harder. So this is interesting because it gives you the perspective of a predictor of what is happening. And here is the final performance. And as you can see, it's actually flying really well. This is something I can't come even close to, and even the best humans have a hard time if we make this fast enough, challenging enough. The behavior it's learned is very, very good. Okay, yeah, I have some questions in the chat, but I think this might be actually a good time to address some of these because next, what I want to do is talk about the COVID-19 pandemic. So let's look at the questions. The problem of learning optimal decisions is similar to causal inference. What are the fundamental differences between causal inference and learning optimal decisions? Yeah, if you can do causal inference, that is great. But what we are trying to tap into are domains that are so complex that you don't have a domain theory, and you can only observe them phenomenologically. And we don't have to come up with explanations of why certain actions work in certain contexts. We only need to know that they do work based on historical data. And that kind of understanding can come later, perhaps. There's one suggestion for future work, and that is that instead of evolving a neural network to do the decisions, make the decisions, we could actually evolve a rule set. And the rule set is interpretable. You can read it, and you can try to understand why those decisions are made. And you could try to get into a causal system. Now, causality is, of course, a complex concept, but at least you would have an explanation in terms of why certain variable combinations work together in order for you to make a decision. But that's the basic idea, that it is certainly fine if you can do it, like simulation is fine if you can do it, but we are trying to be very general and also apply it to very hard decision-making tasks where such domain theories are not available. But you do have data. So like weather prediction is maybe a good example of that. If you can really understand all the phenomena in the weather, you can simulate it accurately and make perfect predictions. But a lot of times you cannot, but you have a lot of data and you can make predictions based on data. You've seen that in these conditions, rain develops tomorrow. And those kinds of predictions are perfectly useful, even if they don't exactly explain how those happen. And that's what we're tapping into. There are lots of applications like that. And there's another one. How do biases in the data interact to affect the evolution of algorithms? Yes, everything comes from the data. You have to have a data set to begin with and to build those predictors. And if you only have data from a very small region, you cannot really make great decisions outside of it. So you have to pay attention to how you build it. So for instance, in the CyberArk domain, planting basil, we started with recipes that people would actually implement, but we also implemented recipes that would be just very different from them. So we have some exploration and some coverage of the space already. And that's something that may be difficult to come by in some applications. But as soon as we start making decisions and making prescriptions, those decisions become data. And we can gradually expand. And this was the story also in the CyberArk domain, that initially we set up some limits, like the lights would be on max 18 hours a day, and then there would be 6 hours of darkness. But evolution very quickly discovered that, hey, I can get better answers, better outcomes if I turn on the lights for 18 hours a day. And we noticed that, and we relaxed that and say, well, have it your way. Turn on the lights for 24 hours. As far as I care, and it turned out that that actually worked beautifully. The decisions, the recipes that were evolved that worked the best had the lights on all the time. Basil does not want to sleep. It wants to produce and grow and become better tasting. But it was a surprise. The biologists in the team did not anticipate that because that's not natural. But it turned out that it was an opportunity to do better than nature, keep the lights on all the time. And that we want to allow that. And it may have to have, we may have to have this kind of a loop be active, and we actively monitor it and open things up so we get enough exploration. But it can be done if you pay attention to it. But a better starting point is if you can have a broad set of examples so that you avoid biases as much as you can. But that's really the power, actually, of the whole approach, that humans have biases, like the 18 hours of daylight. Evolution or machine learning does not necessarily. We can at least avoid them to a much larger extent. And that's the opportunity. We can do better than people because we don't have the same biases, and there may be pay dirt outside of those biases. All right, let's see if there are more questions, but let's move on to the COVID-19 now as a real world application. So this is now taking a problem that, of course, everybody is involved in, and a lot of people tried to work on COVID-19. When we submitted our paper on this to arXiv, I looked around and I recognized that between arXiv and medRxiv, I think there was a new paper appearing something like every 17 minutes on COVID-19. This is the main focus of the entire scientific community right now. So we also wanted to do something in it, but our approach is quite different. A lot of people are working on predicting how the pandemic will unfold. Most of them are standard epidemiological models on steroids, doing it better, which means that you are fitting a mathematical model differential equation to the data. But what we want to do is going beyond that. Like I said already in the beginning, we don't want to just predict. We want to prescribe. How do you deal with it? How do you bring that curve down? How do you do it without closing schools, without a large economic impact? Now, this is, of course, a trade-off. You can bring this down by locking everything down, but it's very high cost. So you need to pick how much you want to balance those objectives. So it's a multi-objective problem between health and cost. But the important part is that we are not just predicting what will happen, but what we should do about it. And that's the new perspective. We haven't really found other people working on COVID doing much of that. Now, first step is still to build a predictor, and we have to do that with available data. So one good part of COVID is that it's happening now when everybody has data and everybody's crazed about data. So there's actually data sets that are available. In particular, the Oxford data set includes the number of cases as well as the non-pharmaceutical interventions, closing schools, reducing transportation, international travel, and so on. And as a matter of fact, I just this morning was in a Zoom meeting with Toby Phillips, and they are continuing, they are updating it weekly, and they are expanding it as new data comes out and new phases develop in the pandemic. So this is very fresh data. They have lots of people, volunteers working on it, and it's hard work. They have to go and look at announcements, newspapers. How do you get this idea of what actually is being implemented in different countries and different states and locales? But the data is available, and of course the case data is available in numerous places. It's also unreliable to some degree. Governments don't always keep up, and they sometimes testing is falling behind, but there's a lot of data available there. Now, the standard compartmental models are 100 years old. There's some developments lately, but they're still pretty much the same. They break the population into compartments, those who are susceptible, those who are infected, those who are recovered, and you can extend to a couple of others. Also you can add a network model on top, like how much interaction there is. The core is to set a bunch of interaction parameters right. And that is very hard to do. And especially when we have these NPIs that are constantly changing, the interventions are changing, you have to do a new model every time. It's very hard to do. So our approach is very different. We are simply modeling the data. Again, it's phenomenological. No causal inference, not even at the level of compartmental explanations, but we're just looking at what the data tells us. And the beauty of it is that no matter what's happening, there can be all kinds of nonlinear interactions where the prime minister tells people something, but then there's a study that comes out in science, and what do people believe? What are the cultural differences on, greetings? And do people more or less follow the community guidelines, or are they very individualistic? All that is actually in the data. It's very hard to take into account in the models, but it is something that affects the data, and we are only observing the data. So we have no assumptions. All the interactions are in the data. Of course, we do need to have a certain level of accuracy, and we have to have a certain level of just volume of data. And initially we were concerned about both of those, but it turns out that it's accurate enough and there's sufficient enough that you can actually do something with it. So the predictor, yes, you predict what will happen in the future. So we have an LSTM neural network to do that, but it wasn't completely easy. The first attempt doesn't quite work. there are some constraints that you want to have. You have a certain population, and eventually there's herd immunity. And if you are implementing interventions, more stringent interventions should have an effect that reduces the cases monotonically. So there are some constraints like that that you want to put into your predictive model to make it more accurate. And we can. So we have one pathway here for just the cases and another pathway for just the MPIs. So there's time series of both over time. We are looking at cases here, but parallel to that, there's the restrictions, the MPIs that are different, that are changing every day. So they form two time series and we bring them together in order to predict. And the predictor, eventually, when we train it, we see 21 days of prior data, and then we roll out the predictions 180 days into the future. So the prediction becomes an actual data for next day and so on. So we kind of rule it as a moving window towards the future. And then on top of that, we are estimating the confidence. This is where we bring in Rio, the mechanism I talked about, using a Gaussian process to evaluate the residuals and errors. And it also had to be adjusted because we have this rollout property. So we start with uncertainty, and then we roll out the Rio distribution and looking at quartiles, upper quartile and lower quartile. It gives us a confidence interval where the actual prediction is in the middle. So a little bit of technology there to bring it, to make it work. But then we have a predictor. How well does it work? It actually works pretty well. And this was really reassuring. So we look at a point in time and our predictions into the future using the predictor, and they are generally quite accurate. And here are just a couple of countries, Italy and Germany, and they follow the path quite well. And this is with the current NPIs. And we are now doing, so this was relatively early in the pandemic, in I think May, so we didn't have really that much choice. There were some countries that were going down, and Germany was doing well, and others were exploding. So across the countries, this kind of a 2-week period at least is pretty accurate in terms of predicting based on a database model, the predictor, which is really nice. And it turns out that the predictor design that we have actually outperformed what we could come up with various other models, simply backprop, random forest, linear, and so on. And the confidence intervals are meaningful, that they actually are what you expect, and what also they are similar to what epidemiological models predict. It's not perfect, but it's at least reasonable. Now the prescriptor, the other side. Okay, we still have time to do the demo too. So this is a more simple neural net because it's really just looking at the context and it's recommending actions in these different dimensions. But it is multi-objective. Each one of these is evaluated according to the number of cases in the future and the stringency of MPIs. So health and cost. And this is evolved. Here's a plot of the evolution, and you can see the Pareto front forming. These are the different trade-offs. There are prescriptors, that minimize the number of cases, and others that minimize the cost. And here we have some of the trade-offs that might be those that we eventually implement. But it's nice to know that that's happening. We are getting a very nice Pareto front. So now let's look at a demo, the interactive demo of this system. You can find it in this website. It's open to the public, evolution.ml. And this is the general idea. We can look at different countries of the world. We are always showing the 20 most affected countries, which actually means that China is no longer in that list. It was originally, even in May still, but no longer is, and many other countries. But these are the big countries now that have the highest number of deaths. We are doing this every day, or as soon as the data is updated. So there's quite a bit of computation, so we have to limit the number of countries where we can do the prescriptors. This one happens to be Italy that we're showing. Sorry, this is US. Yeah, this is US actually. So as you probably know, US had the first wave and then the second wave, and things opened up. And now we are hopefully coping with the second wave. Now, here is the Pareto front. So we are picking a prescriptor that's all the way to the left. Minimize cases at all costs. And if we do that, we can see that the prediction tells us that we can actually get the pandemic under control. But there's a high cost to it. Here below, we have the same timeline, but this is showing the MPIs. And as you see, first there was nothing, and then some of these were brought up now, and some of them had since opened, like workplaces. And this pretty much coincides with what's happening here. And I actually just learned today from Toby Phillips that these MPIs are very, that they are actually plotting, their data represents the MPI in a very stringent manner. If anywhere in the US there's a restriction, it's implemented as for the whole US. So it's a little bit more stringent than it actually was. So our data does not show all the openings that were happening. The Oxford data does not, but that was the cause of this peak. And now what we are recommending with the most restrictive prescriptor is close up everything and you do well. Now we can look at some different trade-offs in this outline. If we go all the way to the right, open up everything, economies, everything. Well, we're not going to do that well. We're going to have a third peak and it's going to be bigger than anything else, 150K cases per day. Pretty bad. So the question is, are there some prescriptors, trade-offs that give us ability to control the pandemic while keeping economy running? And this is one of them, somewhere in the between. It still recommends strong workplace closings, but most of the other possible and public events and very strong public information campaigns like masks in order to keep it in check. We can go a little bit further, I think, before it explodes. So each one of these opens up a little bit more. The curve climbs up a little bit more. And like here is probably where we don't want to go anymore. Almost everything is open except public events and workplaces. But you can also ask a question, we want to open workplaces, what can we do? But that's not in this interface. It's a different research-based interface. We can look at different countries. India, for instance, is still in bad shape. They're still growing. So we got to have a little bit more restriction there. But the idea is that you can get different prescriptions for different countries that work in different countries. Now we are just about out of time and I want to wrap up, but I invite you to try this out. The link is in a couple of slides and you can see how we could actually deal with the pandemic based on this AI, and ESP based AI. So there are a couple of principles that already came out. Schools and workplaces are the most important. That's something that you always have to pay most attention to. And now we are starting to understand that in the real world. People are indoors, they're close proximity, long time, in each case, all day. That's what really matters. Not so much some of the public events, transportation, things like that. Well, public events too, but gatherings and things like that, we can relax a bit. Another interesting thing is evolution is creative. It gives you the idea that you could alternate days when places are open and when they're closed, which is something that people have now suggested. So it's a creative solution. Remember, it doesn't have that much space to explore and recommend things, but this is something it can do, changes over time, and it took advantage of that. And we can also go back in time, and we can find things like in the UK, for instance, there was an opportunity at one point in time where full lockdown would have been avoided. If they had acted early enough, just the school closings could have kept and some restrictions on workplaces could have kept the pandemic in check. And there are also things that we're finding now that cultures are different. For instance, Italy should have done a lot better than they actually did. And the reason is partly because they were early in the pandemic. People didn't really understand yet how serious it was. But also the culture is different from maybe South Korea or China, where the predictions actually borne out much more accurately. And that's something we have to take into account, and we're working on now, having an adherence factor in the prediction that corresponds, it's something that's learned, but it corresponds to the culture. So to wrap up, I think there's an opportunity here to build an AI-enabled society eventually. I've had this slide for a year and a half now in my talks because I really believe in it. that if we can agree what we want the society to be like, what do we value, production, fairness, environment, we can set those objectives and then have AI give us prescriptions of how we should manage a society. Prescriptions that are unbiased, hopefully free of pork and other personal agendas, will give us the best trade-offs, given that we want certain kind of trade-off. And before COVID, we did not have an example. COVID is an example of that. We can come up with these policies. So to wrap up, ESP utilizes surrogate and evolution to do well in these decision-making tasks. And we have a very interesting regularization effect that happens automatically. And as a whole, it demonstrates power of data and machine learning, working in synergy so that we can do something more than what humans can do. And we can make these systems trustworthy and measure trustworthiness so that they can actually be deployed. It's still a long ways from actually having policymakers listen to us and other scientists for that matter, but we hopefully can at least demonstrate that it's possible. So if you're interested, this is the URL for the whole talk, and the COVID is underneath that. Okay, I think we are out of time. Do we have still time for a question or two?
Yes, just one question since we're so much short of time. Does anyone have any questions? Oh, it looks like Wolf. You're free to ask a question.
Sure. Very interesting talk, Risto. Kiitos. I have a question regarding robustness. So imagine, you've learned something and your predictor and prescriptor are optimal, but then something very disruptive happens. A road is blocked, it's never been blocked before. A key employee gets sick. Obviously, a learning system over time will adapt, but a good, robust system will adapt very quickly. Can you maybe talk a little bit about how you handle robustness?
Yeah. Yes. So there's intrinsic robustness, and just because we are training with multiple countries, so that's actually have been the key, and that was a surprise to us. So a lot of different behaviors are there across the world, and the predictor is trained across all of them. So it has seen quite a bit of variety already, and that gives us a little bit of robustness. But on the other hand, we also want to do a little bit of customization at least, so we can cluster the countries so that those that behave similarly are in the same phase of the pandemic. We could train a more accurate model for those countries. But then we lose some of the aspect of the robustness. So that's actually something we are looking at doing now. So we give a baseline of training with everything and then a specialization. So hopefully we don't lose all of the robustness. But there are other aspects of it, and in this particular, some of them it's domain specific, like how much variation can there be? Now, but also just inherently, the data is just unreliable. I mean, we are understanding now that some of the numbers were fudged and others were just facing real obstacles because the collection was so hard. And France does not report numbers on weekends, and then they appear somewhere later. There was a correction of 50,000 cases in the UK when they actually found that they were double counting them. So the data already has a ton of that kind of noise that helps make the training more robust. So what we're most worried about is actual real change that we should have in the model, like an NPI that's encoded differently, should be encoded differently. That's the real challenge. How can, and Oxford deals with that. How do they actually bring the policies of different countries to the same scale? How do they interpret them? That's a work on its own, and it is a big challenge. You're absolutely right.
Thank you. Risto, one question I have. When you're saying that you have slides and such on evolution.ml/ESP, will these slides be on that website too, or did you want to send us those to us separately?
Yeah, they are, yes. And under ESP, there's RL, which is the first part, and then there's MPI, which is the second part.
Okay.
So they're in two files, and the demo is under MPI. You can
Great.
the interactive demo. Yeah.
Great. Yeah, I'm gonna mention this to Peter so that we'll have a link to the slides when we post the video.
Great.
With that, it appears we're out of time, but this was a great talk, and I look forward to talking to you later today, Risto.
Yeah, me too.
Great. And with that, Peter, you're free to stop recording now. And I'll see everyone next week.